Hello, welcome back to Introduction to Semiconductor Devices. We are now in seventh week of the course. So we are more than halfway through what we wanted to cover. And in the last week, we were discussing the operation of mass capacitors. We looked at the depletion, inversion, and accumulation regimes. And we understood them based on simplified band diagrams. We just looked at the semiconductor part of it, right? So today we would like to go deeper into understanding the electrostatics of mass capacitor. And to do that, let's start with the basic bands. So this we have done even for the metal semiconductor junctions. So we have semiconductor, which is having the EC and EV, the conduction valence bands, and then there's a certain Fermi energy. And we have seen already that the electron affinity of a silicon, in this case, is I think about 4 eV, 4.01 eV. So 4 eV, let's take it with that. Okay. So, and the electron affinity is essentially the energy difference from the conduction band edge to the vacuum level, right? We've seen this definition before. And this is a p-type silicon. Okay. And now we also have an oxide in between. Between the metal and the semiconductor, we have an oxide. And we know that oxide has a large band gap of 9 eV. This is silicon dioxide, so 9 eV of band gap. And then it also has an electron affinity, which is shown here, the distance of the EC from the vacuum level. In this case, for silicon dioxide, it turns out to be 0.95 eV. So it's actually, the electron affinity is quite small. Okay. Then we have the metal, which has its own Fermi energy, EFM. Okay. So, we can define the work function of a semiconductor, phi s. Okay. If it's a p-type semiconductor, you could easily define it as simply it's essentially the distance between the Fermi energy to the vacuum level. So for a p-type semiconductor, it's going to be simply the electron affinity plus Eg by 2, and I'll call this distance of Fermi energy from intrinsic level as EF. Okay. This is I'll call as EF. Sorry, phi f, not EF, phi f. Okay. So this distance. So basically, this is for a p-type semiconductor. If it was an n-type semiconductor, if you're using, that means a PMOS device, if you're using, this would be chi plus Eg by 2 minus phi f for an n-type, right? Because for an n-type semiconductor, the Fermi energy would be somewhere here, and this would be your phi f. So you plus Eg by 2 minus phi f would give you the work function of the semiconductor. Okay. So there is a, right now we have not really considered that they are in contact. We are still looking at all this metal semiconductor, silicon dioxide, slightly far apart, right? So we can define an important parameter which we call as phi ms, which is essentially the work function of metal minus work function of semiconductor. So this is phi ms. And this is an important quantity that we need to look at. When we talk of thresholds, we will introduce this again. But in our previous lectures, we have looked at an assumption. We said that for an ideal mass capacitor, the phi m is equal to phi s. The work functions are same for metal and semiconductor. Okay, so this is equal to 0 for ideal MOS devices. But you will almost never have an ideal scenario because you see phi s is dependent on doping, right? So this has a this one. So the work function of a semiconductor is dependent on the doping density, and you will have different varying amounts of doping, and because of that, phi ms is going to be varying even if you just take the exact same metal, right? So it is never going to be 0 for all the devices. It's going to be some number. Okay. But right now we don't want to worry about it. We want to simplify our analysis. So for today, we will assume that phi ms is 0. All right. Now, if phi ms was 0 and you don't apply voltage, what happens when you bring them in contact? Right? We have to when we bring them in contact, essentially, the first thing we have to do is draw equilibrium Fermi level, which is a straight line. Since there's no applied voltage, implies EF is uniform, right? Applied voltage is 0 implies EF is uniform, right? That was the first step in drawing band diagrams all the time. Once you do that, you draw the EC and EV at appropriate distances. Okay. So one important thing to make sure is the distance of the electron affinity is basically known, right? So basically this is 4 EV. If I put a vacuum level here, so this is 4 EV and this is 0.95, right? So basically this particular barrier here is going to be 3.05 EV. Okay. And this is the energy band gap. This is 1.1 EV. Just please remember, these diagrams are not drawn to scale. If I were to draw to scale, then this region has to be 1.1. So this has to be 3 times this. So I'm not drawing to the scale. Okay, just indicate if these are our distances. But you need to remember that this barrier is 3 times almost, slightly less than 3 times the energy band gap. Okay, so it's quite large barrier. Similarly, on the lower side, you have a barrier. So this will be, roughly something number between 3 to 4 EV, some number between that. Okay, depending on the band gap, you can calculate. So what does this mean? Well, this is an insulator, right? We know that silicon dioxide is an insulator, and we see that if there are, let's say, electrons in the conduction band of silicon, they see a 3 EV energy barrier, which is a very substantial amount of energy barrier. That is why electrons cannot go into the metal. Okay, that is why it behaves as an insulator. Similarly, if you have holes in the valence band, they too see a energy barrier of about 3 to 3.5 or so EV, right? So they also cannot go into the metal. Or rather, metal cannot. Electrons cannot come in here. Okay. So because of that, oxide acts as an insulator, right? Because of energy barriers. Oxide is insulator because of energy barriers in EC. For energy barriers, I would say for electrons and holes, okay, to move into metal. Okay, and we have briefly mentioned the problem of energy barrier, right? So wherein if you have a barrier like this, the height of the barrier we know, 3 EV in this case, and the width of the barrier will be the thickness of the oxide. Okay. So because of that, you can analyze and see what happens. And if the thickness is large, if it's 10 nanometers, it's almost like a perfect insulator. But the moment the thickness reduces, this MOS capacitor starts having leakage because electrons will tunnel across the barrier. Okay? The tunneling current becomes significant. That is the reason why the leakage current increases. Okay, and the MOS device does not work as a proper capacitor because of the leakage. Okay. All right. So this is the basic background. So let's try to analyze what happens when you have a MOS device in accumulation. Okay. Let us start with the NMOS device. That means I'll start with the PMOS P-type substrate. Okay. So let me draw the EC, EV. This is my EV. This is my EC, and it is NMOS device. Okay. So I'll anyway draw the Fermi energy just for reference. Equilibrium Fermi energy. If there's no applied voltage, it will be like this. So you have a P-type device, but we are saying that we want to study how the NMOS device works in accumulation. And if you want to accumulate it, what is the type of voltage we need to apply? So this is a P-type substrate which has holes, and we want to increase the number of holes. right? So we want to bring more holes near the interface. That means we have to apply a negative voltage. If you have to apply negative voltage, what do we do? The Fermi energy shifts up whenever you apply. So essentially we are applying a voltage with respect to the bulk. Let's say this bulk is, this is grounded, and you have a metal here on this side, and we'll apply voltage. I'll just show that. So let's say this is my EFM, okay, and this is my applied gate voltage, Q times VG. If the applied gate voltage is negative, the Fermi energy moves up relative to the bulk Fermi energy, right? And that's why you see this. And what happens to the bands? Well, the bands, we know that there is more of holes in the interface, so we'll put them like this. Okay. So, and what will happen to the oxide bands? The oxide band gap has to still remain 9 eV. So what we'll do is, what type of field should be there in the oxide? All the time we have to think about how the field should be. That will simplify our analysis. Okay. So now you have positive charge, right? Here you have positive charge. Holes have accumulated. On the other side, you have to have negative. You're essentially putting a negative bias. So there will be electrons on this side. So basically your electric field is in this direction, from right to left. And so because of that, my oxide, I will, oxide will bend this way. Just to indicate that this is essentially showing the gradient. Gradient gives the electric field, right? Electric field. And in this case, it is negative. Remember why it is negative, right? So this is a band diagram, for a NMOS device in accumulation. Okay. So to understand these devices, well, we will try to draw what are called as block diagrams, block charge, field, and potential diagrams. Okay. So essentially, what we can do is here, we know that there is a positive accumulation, positive charge, right, at the interface. So I'll represent this by putting a small block here. This is holes. Okay, accumulated at the interface. Right, this is holes accumulated at the interface. Let's say if this is, I'm sorry, I should actually make it positive. Okay, this is a positive charge, so I'll draw this is holes at interface. So this is plus Q charge. So since it's a capacitor, there has to be equal and opposite charge on the metal plate. So that also will be at the interface here. Minus Q charge, right? So what is the thickness of these charges? This, if I took a look at these two charges, right? What is the thickness? Well, these are like infinitesimal sheets, basically. So negligible thickness. Why should they be negligible? Just at the interfaces, interface between silicon dioxide and metal, we have a negative charge. At the interface between silicon dioxide and silicon, we have the positive charge. Why should they be negligible thickness? Well, I mean, we know that the electric field inside the metal cannot be non-zero, right? It's zero. The thickness of the metal is such that the potential is same everywhere, and then the electric field has to be zero, right? So if I draw the electric field, I know that this is here 0. And even in the silicon, it is 0 because it's a, lots of holes and they behave like effectively like a metal, pseudo metal, right? The semiconductor behaves like a metal, almost like a metal. There's going to be a small electric field, but we can neglect that. So basically electric field is E is 0 here in both these locations. Okay. Remember, if there was an electric field, the charges will reorient because they're all free charges. Holes in the p-type semiconductor and electrons in the metal, they're free charges. They can reorient in such a way that the electric field is killed. So there cannot be any electric field in the bulk of a metal, right? So that's why our charge exists only at the interface. So even though I'm showing this, blocks to be a finite thickness, for all that's only a visual way of representing it, but it is understood that they are very right at the interface. Okay. All right. So yeah, you have equal and opposite charges. So there should be a capacitance. So what is the capacitance? Okay. So the capacitance you can think of C accumulation, CACCL, right? Okay. C accumulation should be equal to simply the, you have the oxide and essentially the oxide capacitance, right? So we'll take it as C oxide because if you have, charge plus Q and minus Q separated by distance, we know the capacitance already. It is simply going to be epsilon oxide divided by the thickness of the oxide. Okay. And by the way, remember that this is in farads per centimeter square. Okay. We are always dealing with per unit area capacitances. Okay. All right. So we have the capacitance and we have the field in the metal and the semiconductor. What is the field in the oxide? Well, whenever we know, we have mastered this recipe. Whenever we want to find a field, we need to solve the Gauss law. So dE by dx should be equal to rho. But in the bulk of the oxide, there are no charges, right? Because, in between, the thickness here in this region, there are no charges. We have made that assumption when when we talked about the ideal mass capacitor, right? So we said there are no fixed charges. This is because no fixed charges in oxide, right? Inside the oxide, there's nothing. So that means E has to be constant, right? Will it be 0? Because outside it is 0. Will it be 0? Well, it cannot be 0. The reason is we know that there is a positive and negative charge, right? And always when we mentioned that there is a sheet charge here, right? This is a sheet charges, right? So whenever you have a sheet charge or a charge discontinuity, the boundary condition tells you that if you have two sides, E2, okay, this is boundary conditions for E field, right? Normal component, of course, here, okay? So if I have two regions, E1, E2, and I'm looking at the normal component, okay? Okay, normal component only I want to look right now. Okay, if I have this scenario, what is the relation between E1 and E2? Well, you know that E2 minus E1 should be equal to sigma by epsilon naught, right? So we can prove this based on Gauss law, okay? Gauss theorem. If you take a Gaussian pillbox and then look at how the electric field is. So only on the top and the bottom faces of the cylinder you can have non-zero contribution of flux. So that will give you this, okay? So essentially, this discontinuity in the electric field is sheet charges, okay? Sheet charge. Okay. So because of that, E field cannot be 0 in the oxide, but it has to be a constant. And we know that constant has to be, just by looking at this picture, we know that electric field is actually going from right to left. So we will take it to a negative number. And I will erase this bit here. Okay. And I'll show that electric field is essentially going to be something like this. Here, E field is constant. So this is how electric field looks like in a MOS capacitor. Right? Now, we would also like to analyze what is the potential. Okay. And whenever we want to take potential, we take some reference. So let us take the potential in bulk is 0. Let us take this as a reference. Bulk, we keep it 0 and we see what happens. And and there is no electric field in the silicon, so potential is going to be constant. But when you come to the oxide, there is a constant electric field, so there should be a linear potential, right? And considering that it's a negative field, it should be like this. Okay. Therefore, what essentially we are saying in this diagram is that this voltage is VG. Whatever gate voltage you apply, that voltage, negative voltage we applied, that's why we are showing it in the negative axis here. Is this correct? Yeah. Gradient is positive, but minus of that, so yeah. So yeah, correct. Okay. So we are applying a negative voltage, and then that voltage is dropping across oxide, and by the time you reach the interface between semiconductor and silicon dioxide, it is falling to 0. So we can easily know, right? We know the relation E is equal to minus dV by dx. So in this case, gradient is positive, so electric field is negative, so it's consistent. Okay. So this is how your device works. Okay, this is the electrostatics of the device. And the reason I'm taking this time to do it in depth is you should be comfortable with this process thinking. Once you are clear about what is happening, the way to analyze MOS devices, you will see that the physics is quite simple. The band diagrams become very, very simple, right? So because you see, the moment you see a band diagram like this, you know that electric field is constant and it is negative. Here also, it's constant. I mean, well, actually, I'm sure this is very, very small region. This is not going to be. This is, it seems like it's some kind of negative field, but the distance is very small. Okay. This distance is going to be negligible. I'm just amplifying it. Okay. And then metal is here. Okay. So this is how a NMOS device works in accumulation. So please take your time, work through it, make sure that you're comfortable with this. In the next video, we will talk about NMOS device in depletion. I'll see you then. Thank you so much.